Hello everyone. This experiment is the interference and diffraction of light. Diffraction and interference is a typical property of a wave. The fact that light displays diffraction and interference is evidence that light is a type of wave. By studying the diffraction and interference pattern, we can figure out the wavelengths of light. Today we will study the single slit diffraction and the double slit diffraction interference of light. And this is the system we're going to use. Left side we have 4 single slits and 4 double slits. And the number here 0.0 to 0.004 units millimeter. These are the slit widths. In this experiment, we use letter A to represent the slit width. And for the double slits, the bottom row that tells us the distance between the slits. That's D. For example, the first pair, D equal to 0.25 millimeter. So today we will study red light. So there is laser coming out from this part, and you have a screw in the back. You can move the light left, right, up and down. And we let light pass through the aperture here, and we can insert the single slits and double slits here. So you hear the click, and there is a number we can read here. That's 0.02. That means I'm using the first single slit. And all the board, now we roughly see the pattern. I will turn off the light later. The first measurement is to find out the distance from the slit to the screen. On the bench we have a ruler there, so we can read the position of the slit. That's about 27, and this side is 122, and plus the distance from the screen to the bench. So I used the total distance is about 102 centimeters. There are 3 parts in this experiment. Part A is the single slit diffraction. Part B, double slit interference. Part C, we will study the diffraction pattern due to a hair and find out the thickness of the hair. Next, I want to show you how to collect the data for the single slit diffraction. So I will turn off the light. This is the diffraction pattern due to the first single slit, and we want to measure the width of the central brightness. And to do that, I'm going to mark a line along the minimum or both sides of the central maximum. So I'm going the middle of the dark line. So I'm going to write down this is the 1. So next I'm going to change to the second slit. So the slit width will be doubled. So let's see what happened to the pattern if I double the slit width. Now you see the difference. The second slit is wider, but the pattern is narrower. Again, I want to measure the central width. So I will mark the position, the dark line, the middle of the dark line on both sides of the second one. So we'll label this as 2. And the third one, again, this one will be the slit width, the third one, 0.08 millimeter. So now it's getting narrower and narrower. This is the last one. So now you see the slit width is about 0.16 millimeter. And the L, the distance from the screen to the slit, is about 1.02 millimeter. Now you see how small the diffraction pattern. This is the mark I made for the single slit diffraction. So I used the L equal to 102 centimeter. And next we want to measure the distance of central maximum. Basically, that's for the first slit, that's the distance between the first pair of line. and this is for the second pair, third pair, and fourth pair. For example, I measure the distance between the two lines, and the distance for the first single slit, that's 7.6 centimeter. And I repeat for the other three pairs. This is the data I got. Next, I will show you how to collect data for the double slits interference. Now this pattern in the first pair, and you see the envelope due to the diffraction, and also you see the tiny dots in each part. And for this pattern is caused by a double slit. The distance between the slits are like 0.25 millimeter, and the slit width of individual slit is 0.04 millimeter. And to collect data, I'm going to mark the center of each bright dot. So center of each bright dot. And I will make a label on the center bright dot, and that's m equal to 0. So this is the first pattern, and I will make the same. This is due to the second slit. The slit width is doubled, and when if you look at that, when the slit distance between the two is doubled, the distance between the tiny dots is getting closer compared to the first pair, and it's very hard for me to mark the line, so I will skip this one. And the next one will be the individual slit widths will be doubled, but the distance between slit will still be 0.25 millimeter. Now you see this one will be much easier, and I will mark the center bright dot. So this is the m equal to 0, and then I have m equal to 1, 2, 3, -1, -2, -3. Next, I'm going to show you how to collect the data for double slits interference. Now you already see the pattern for the first pair. You see the tiny bright dot. I'm going to mark line at the center of the bright dot. This is the double slit interference for the second pair. Now you see it's very hard to see through the camera the tiny dots. So I will not collect data for this one, but I just want to show you how the pattern looks like. Very, very tiny dots. So this is the second pair. This is the double slits interference for the second pair double slit. It looks like this one will be a little bit easier. I'm going to mark here, and this is my central maxima. I will label it 0, and then this is the diffraction pattern for the fourth pair. It's very hard to see the tiny dots in the central maximum. And again, I just want to show you the pattern. I'm not going to collect the data for this one. This is the data I got for the double slits interference. So you see the line I marked here is the center of each bright dot. And I also labeled m equal to 0. This is the center of the central tiny dot, m equal to 0. To the right, m equal to positive 1, 2, 3, 4, 5, 6. Left side is negative. And this time I'm going to measure the distance of each order with respect to the central line. So for example, here I want to measure m equal to 1. And from here, m equal to 1 is 0.3 centimeter. And you repeat the same for m equal to 2, 3, 4, 5. So to the right side, they are all positive. And to the left side, when m is negative, ym is also negative. And I recorded the data for the first set, and for the other sets, it's hard to measure, or they have a less number of data points. The last part of this experiment is to observe the diffraction pattern due to hair. So now I removed the slit system and I placed a hair in front of the aperture. Now you see the red dot, that's a reflection due to the hair. And we will observe the pattern on the screen. I will turn off the light. Here is the diffraction due to hair. Look at that. Very similar to the single slit diffraction. By observing this pattern, we can figure out the thickness of the hair. And to do that, I'm going to mark. We will measure the slit central brightness width. I will mark a line. This is the data I got for the hair diffraction. The two vertical lines, each one was marked at the center of the dark dot, right next to the central brightness. And the distance between these two lines give us the width of the central bright spot. And I got 3.4 centimeter here.